8.2 kiloyear event. The 8.2 kiloyear event appears as a dent in the warm Holocene period. Evolution of temperatures in the post-glacial period following the last glacial maximum, LGM, according to Greenland ice cores. 1. The warm Holocene period with the 8.2 kiloyear event. Central Greenland ice core reconstructed temperature up to mid-19th century. In climatology, the 8.2 kiloyear event was a sudden decrease in global temperatures that occurred approximately 8,200 years before the present, or c. 6,200 BC, and which lasted for the next 2 to 4 centuries. It defines the start of the North-Grippian Age and the Holocene epoch. The cooling was significantly less pronounced than during the younger Dryas cold period that preceded the beginning of the Holocene. During the event, atmospheric methane concentration decreased by 80 ppb, an emission reduction of 15%, by cooling and drying at a hemispheric scale. Identification. A rapid cooling around 6200 BC was first identified by Swiss botanist Heinrich Zoller in 1960, who named the event the Misox Oscillation, for the Valmeselsyne. It is also known as the Finse event in Norway. Evidence for the 8.2 Ka event has been found in speleothem records across Eurasia, the Mediterranean, South America, and Southern Africa and indicates the event was globally synchronous. The strongest evidence for the event comes from the North Atlantic region. The disruption in climate shows clearly in Greenland ice cores and in sedimentary and other records of the temperate and the tropical North Atlantic. It is less evident in ice cores from Antarctica and in South American indices. The effects of the sudden temperature decrease were global, however, most notably in changes in sea level. Cooling event. The event may have been caused by a large meltwater pulse, which probably resulted from the final collapse of the Laurentide ice sheet of northeastern North America, most likely when the glacial lakes Ojibwe and Agassiz suddenly drained into the North Atlantic Ocean. The same type of action produced the Missoula floods that formed the channeled scablands of the Columbia River Basin. The meltwater pulse may have affected the North Atlantic thermohaline circulation, reducing northward heat transport in the Atlantic and causing significant North Atlantic cooling. The Atlantic meridional overturning circulation, AMOZ, weakened by 55%, or 62%. Estimates of the cooling vary and depend somewhat on the interpretation of the proxy data, but decreases of around 1 to 5 degrees Celsius, 1.8 to 9.0 degrees Fahrenheit, have been reported. In Greenland, the event started at 8175 BP, and the cooling was 3.3 degrees Celsius, decadal average, in less than 20 years. The coldest period lasted for about 60 years, and its total duration was about 150 years. The meltwater causation hypothesis is, however, considered to be speculation, because of inconsistencies with its onset and an unknown region of impact. Researchers suggest that the discharge was probably superimposed upon a longer episode of cooler climate lasting up to 600 years, and it was merely one contributing factor to the event as a whole. Further afield from the Laurentide ice sheet, some tropical records report a 3 degrees Celsius 5.4 degrees Fahrenheit cooling, based on cores drilled into an ancient coral reef in Indonesia. The event also caused a global CO2 decline of about 25 ppm over about 300 years. However, dating and interpretation of other tropical sites are more ambiguous than the North Atlantic sites. In addition, climate modeling shows that the amount of meltwater and the pathway of meltwater are both important in perturbing the North Atlantic thermohaline circulation. The initial meltwater pulse caused between 0.5 and 4 m, 1 foot 8 inches and 13 feet 1 inch, of sea level rise. Based on estimates of lake volume and decaying ice cap size, values of 0.4 to 1.2 m, 1 foot 4 inches, 3 feet 11 inches, circulate. Based on sea level data from the Mississippi Delta, the end of the Lake Agassiz Ojibwe, LAO, drainage occurred at 8.31 to 8.18 Ka and ranges from 0.8 to 2.2 m. The sea level data from the Rhine-Meuse Delta indicated 2 to 4 m, 6 feet 7 inches, 13 feet 1 inch, of near-instantaneous rise at 8.54 to 8.2 Ka, in addition to normal post-glacial sea level rise. Meltwater pulse sea level rise was experienced fully at great distance from the release area. Gravity and rebound effects associated with the shifting of water masses meant that the sea level fingerprint was smaller in areas closer to the Hudson Bay. The Mississippi Delta records around 20%, Northwestern Europe 70% and Asia records 105% of the globally averaged amount. The cooling of the 8.2 kiloyear event was a temporary feature, but the sea level rise of the meltwater pulse was permanent. In 2003, the Office of Net Assessment, ONA, at the United States Department of Defense was commissioned to produce a study on the likely and potential effects of a modern climate change. The study, conducted under ONA head Andrew Marshall, modeled its prospective climate change on the 8.2 Ka event, precisely because it was the middle alternative between the younger Dryas and the milder Little Ice Age. Effects. Across much of the world, the 8.2 Ka event engendered drier environmental conditions. Northern Hemisphere monsoon precipitation declined by 12.4% for every degree C of global mean temperature change, while Southern Hemisphere monsoon precipitation rose by 4.2% degree C. The 8.2 Ka event was also associated with an increase in ocean salinity and terrestrial dust flux. North Africa and Mesopotamia. Drier conditions were notable in North Africa. The area around the Charef River in eastern Morocco records an episode of extreme aridity around 8,200 BP. East Africa was significantly affected by 5 centuries of general drought. In West Asia, especially Mesopotamia, the 8.2 kiloyear event was a 300-year aridification and cooling episode, which may have provided the natural force for Mesopotamian irrigation agriculture and surplus production, which were essential for the earliest formation of classes in urban life. However, changes taking place over centuries around the period are difficult to link specifically to the approximately 100-year abrupt event, as recorded most clearly in the Greenland ice cores. In particular, in Tel Sabi Abayad, Syria, significant cultural changes are observed at c. 6200 BC. The settlement was not abandoned at the time. Madagascar. In northwestern Madagascar, the 8.2 Ka event is associated with a negative delta 180 excursion and calcite deposition, indicating wet, humid conditions caused by the southward migration of the ITCZ. Summer monsoons in the southern hemisphere likely became stronger, contributing to precipitation increases. Humidification was two-phased, with an 8.3 kiloyear sub-event preceding the 8.2 kiloyear sub-event by about 20 years. Europe. The sediment core records of the Fram Strait show a short-lived cooling during the 8.2 Ka event superimposed on a broader interval of warm climate. In western Scotland, the 8.2 Ka event coincided with a dramatic reduction in the Mesolithic population. In the Iberian Peninsula, the 8.2 Ka event is linked to greater summer aridity that caused an increase in the frequency of fires and a consequent expansion of fire-resistant evergreen oak trees. North Asia. Lacustrine sediment records show that western Siberia underwent humidification during the 8.2 Ka event. South Asia. Carbonates from Riwasa Paleolake show a weakening of the Indian summer monsoon, ISM, synchronous with the 8.2 Ka event. Stalagmites from Kotumsar Cave and from Socotra and Oman further confirm the ISM precipitously diminished in strength. East Asia. A sediment core from Lopner in the Darim Basin shows a major dry spell occurred during the 8.2 Ka event. The impact of the 8.2 Ka event on forests in the Korean peninsula was severe, shown by a sizable reduction in pollen production. It took approximately 400 years for forest ecosystems to recover from the event to their state before the climatic perturbation. Southeast Asia. Evidence from the Gulf of Thailand reveals that a sea level drop occurred concordantly with the 8.2 Ka event. Also detectable from palynological and sedimentological records is an increase in runoff. North America. In Greenland, the 8.2 Ka event is associated with a large negative spike in ice core delta 180 values. The waters off Cape Hatteras experienced a major salinity increase. Bat Guano delta 13C and delta D values in the Grand Canyon declined. Southwestern Mexico became significantly drier, evidenced by the interruption of stalagmite growth. In the Gulf of Mexico, Bayhead deltas backstepped as sea levels rose. Mustang Island was breached and ceased to be an effective salinity barrier. Gulf of Mexico delta 180 water values dropped by 0.8%. South America. The South American summer monsoon, SASM, drastically intensified during the 8.2 Ka event as revealed by sediment records from Jarea Paleolagoon.